Good morning. I woke up this morning thinking I can't really progress with what I'm doing until I've got at least one complete example. Right now, it seems that I've succeeded in finding the Jacobian right here, del x, del x, del r, del x, del theta, del y, del r, del y, del theta, for partial frac x, y, and r theta, but I really need to make sure we have the inverse for that as well, which would be like del r theta del xy. Remember, this comes from the idea of going around a circle with x being that way, y being that way, and let's say r going this way, and theta being some angle in here, theta, and then that gives the relationship between these three variables, or four variables. But we should also be able to go the opposite direction. R is the square root of x squared plus y squared, and theta is going to be, I'm not sure if there's any algebraic way of writing this, so let's move that down here where I have more room. Theta is arctangent of y over x if x is greater than 0, and it's arctangent of y over x plus pi, or plus 180 if you're using degrees, if x is less than 0. Now the reason for that is that, say, this line here that is already in sort of an orangish color, well, I just changed the color. Okay, it's the same as that line there, but those are not going to be the same angle. This is going to be theta, and going around there, let's make this that gray color too, going around there, that is pi. So if x is less than 0, it's the same as whatever slope is up there, but it goes the opposite direction, which is a difference of pi in the angle. So to me that creates some difficulties that I'm not sure exactly how to handle. So what I'm going to do is guess that I can essentially take an inverse. What I'm going to try, though I'm not sure if this will work, is to take an inverse of our original Jacobian for our partial fraction xy r theta, which was, well, it was this thing right here. If I recall correctly, the inverse of a matrix is equal to the transpose of its cofactor matrix divided by its determinant. For 2 by 2 matrix, in practice, that's just a matter of swapping these two numbers, so AD becomes DA, and taking negatives of these two numbers, so B and C become negative B and negative C, and then the determinant is just AD minus BC. And see, if I multiply this out, AD minus BC, then AB minus AB is just 0. CD minus CD is 0. And negative BC plus B plus AD, negative BC plus AD, all of that is divided by AD minus BC, which is 1, 0, 0, 1, which means that this matrix is the inverse of this matrix. So I'm going to do the same thing with this matrix, which will be swapping these two values. So I'll have r cosine theta and cosine theta, and then taking the negatives of these. positive r sine theta and negative sine theta. And that should be the inverse of that. But then I have to divide by the determinant, which will be r cosine squared of theta minus r sine squared of theta. No, minus negative r, so it'll be plus r sine squared theta. So good news, the determinant has a very simple form in terms of r. So because cosine squared theta and sine squared theta is 1, this will just be divided by r. So I'll be dividing everything by r. I'll have cosine theta, sine theta, negative sine theta over r, and cosine theta over r. Let's test that, make sure that I did everything correctly. Copy that. Whoops. Copy that down here. And copy that down here. Then we'll take these two times these two. Cosine squared theta plus sine squared theta is 1. And take these two times these two. Cosine theta sine theta minus r over r sine theta cosine theta is 0. And we'll have sine theta cosine theta minus r over r sine theta cosine theta will be 0. And then we'll have sine theta r cosine theta times sine theta cosine theta over r, which is sine squared theta, plus r over r cosine squared theta is 1. So yes, this is definitely our inverse matrix. But what I want to do is express it in terms of del r theta del xy, so that when we multiply this thing, this we remember was del x comma y del r comma theta, and this was down and this was across because the x was going down, the r's were going across. So this thing is going to have to match up with this going to the right and that going down. There's one other adjustment to this. I'm going to replace cosine theta with x over square root of x squared plus y squared, and sine theta with y over square root of x squared plus y squared. And I'm going to replace r with square root of x squared plus y squared. So when I do that, this just this part of it is going to be cosine theta, which is x over square root of x squared plus y squared, sine theta, which is y over square root of x squared plus y squared, negative sine theta over r, which is going to be negative y over x squared plus y squared, and cosine theta over r, which is going to be x over x squared plus y squared. Now I can confirm these top two. The top two are going to be, or can I? This is going to be del r del x, del r del y, right? I can confirm those top two, except now I realize that I have put my arrows in wrong. What made me think that? Oh, yeah. I goofed up on those arrows. That should have been down, and that should have been across. Because the r theta here to the right has to match up with the r theta here to down. So that's what I messed up. But otherwise, I can confirm that this is del r del x by taking the derivative of square root of x squared plus y squared del x, which is the derivative, which is going to be, okay, the derivative of x squared plus y squared to the 1/2, and the derivative of that with respect to x is 1/2 of x squared plus y squared to the negative 1/2 times 2x, which is x over square root of x squared plus y squared. So I can verify that that derivative, del r del x, is equal to x over square root of x squared plus y squared. On the other hand, as far as del theta del x goes, with that being the derivative with respect to x of arctangent y over x, when x is greater than 0, and arctangent of y over x plus pi when x is less than 0. Sorry, my calculus skills are pretty primitive. I don't know how to get that, but I think I'm going to trust for now that it does come out to be negative y over x squared plus y squared and x over x squared plus y squared. But let's see what those come out to be in trig. Y over square root of x squared plus y squared. If we expressed all of these in terms of their, what do you call it? Well, in terms of r and theta, this is cosine theta. This is sine theta. This is negative sine theta over r. I feel like I just wrote that. Oh, yeah, I did just write it. And this is cosine theta over r. And because I had it, I wrote it up here. I'm just transferring back. I'm recovering information I've already done. I'm just saying that I would like some kind of other justification for saying that this is del theta del x, and this is del theta del y. So I guess at least I could do a physical interpretation. Let's look at imagining a circle, and I'm up here, say, and I want to change x. I'm changing x. There we go. I go from, there's my del dx, and I want to see how that changes theta. Now, if we're constrained to the circle, which apparently that's where that comes from, is we're leaving that, we're making it so it's constrained to the circle implicitly, then theta goes from there to there. So it, as x goes up, theta goes down, which explains where that negative sign comes from. As r stays the same, and sine theta is probably not a great thing to describe with this diagram because I drew the top of this circle very flat, and that causes a sudden drop here at the end, which makes it be counterintuitive for this example. What should be happening? Well, actually, I'm beginning to wonder if I have it right again, because I'm seeing some counterintuitive things coming up. I want to analyze the question of the circle, what should dx do, using some kind of form that's a little bit like that, using that as our motivation, our to inspire us is what should be happening. But think about this. Let's do del theta del x from here, where x is going from here to here, and this is dx, and theta is going from pi over 2 to some new to pi over 2 plus d theta. We'll put in our actual change in angle right there, d theta. It's going to be a positive number, I would think. No, it's going to be a negative number because theta goes that way. So since theta is sliding over to the right, this will be a negative number. So what are sine theta and cosine theta? Sine pi over 2 is, okay, sine pi over 2 is 1, and cosine pi over 2 is 0. Now my intuition currently says that if I move this a little bit here, the del theta del x is going to be approximately dx over r. Because if r is very small, then a small change in x is going to create a large change in theta. If r is very large, a small change in x is going to create a very small change in theta. And I think that if you make sine theta smaller, if you bring it over here, I think that sine theta would go on the bottom of this. And I need to write this in proper calculus terms. d theta dx del theta del x. So I am thinking del theta del x would be 1 over r sine theta. But that's not what we got, is it? We got del theta del x is negative sine theta over r. The r seems in the right place. The sine theta seems backwards. Let's see, either my intuition is wrong, my math is wrong, or my context is wrong. With context, maybe the constraint to the motion on the circle is in error. For context, maybe the constraint to motion in a circle is in error. Because I'm imagining del x del theta, and I'm imagining that we're changing that x and staying on that circle. Does this partial derivative imply staying on the circle and that r remains constant? On first thought, I'm pretty sure that it does. Let me write it this way. Partial theta partial x means what happens to theta when r is constant, dr is constant, and partial r partial x would mean what happens to r when dx is constant, or when x is constant, when change in x is 0. But let me introduce the other alternative before patting myself on the back. What if del theta del x means the change in theta when y doesn't change, and del r del x dy equals 0. Del r del x is the change in theta when dy is 0. Okay, what would that mean? We would have, okay, I've run out of room at the bottom. So let's imagine things in that alternative context. We are having an incremental change in x, but this time, instead of having the particle stay on the circle, we are actually changing both the angle and the radius. So when we move to a new spot, oh my goodness, I have drawn that other circle way too big. We're changing x from there to there. That's not good. I need two really, really, really close circles. Let me try that again. Actually, I don't think I can even draw the circles that I want to be drawing. We'll just pretend for the moment that this is a level line between here and here. We're going to say dy is 0. So I'll just draw it like that. I'll make it a really thick line. I don't know. Maybe that's not scientific. But the point is, we're changing x. We're not allowing y to change. Okay, I got a better idea. I'll draw, instead of trying to draw it up here, I'll draw it down here. So we're going to change x without allowing y to change. So here's our initial x, here's our new x. We're going to change both. We are allowing both r and y to change, r and theta to change. So we're not constraining it to a circle, but this is our initial r theta, this is our final r theta. And what we want to check is whether del r del x is cosine, I think it was cosine theta and negative sine theta over r. Yeah, del r del x, del theta del x goes down, del r del x, del theta del x, which was cosine theta and negative sine theta over r. Okay, it's beginning to look like my initial conceptual constraint that the radius didn't change was flawed, and this one, that the y value doesn't change, is going to work. Okay, my apologies for the confusion, but now I can see how easy it is to make the mistake of holding the wrong thing constant conceptually when trying to interpret the meaning of a partial derivative. Okay, you can see here when sine theta is small, x changes, but theta barely changes at all. As sine theta gets bigger, the change in x causes a greater change in the angle. This continues up the circle. Sine theta gets bigger, the change in x causes a greater and greater change in the angle, until the very top of the circle, where sine theta is 1, and you get a maximum possible change of theta out of a change in x. So, in summary, I think we've managed to find the Jacobian and the inverse Jacobian for this expression when x, y, r, and theta are defined as your standard Cartesian and polar coordinate systems. By doing the inverse of a 2 by 2 matrix, I was able to get around doing the derivative of an arctangent. For some people, it might be preferable to do the derivative of the arctangent, of course. So perhaps it's easy if you know how to do it. Or without even knowing how to do it, a quick Google search can lead you to someone saying, I know that the derivative of arctangent of x is 1 over 1 plus x squared. I'm thinking if you want the derivatives of the arctangent of y over x, you could perhaps use the chain rule. The derivative of y over x with respect to y is simple enough. It's just 1 over x. And this term here can be simplified to x squared over x squared plus y squared, which yields x over x squared plus y squared. That's a good sign. I think that's what we had. And this one, the derivative of yx to the negative 1 with respect to x is, it's negative yx to the negative 2, right? So taking that and multiplying that by x squared over x squared plus y squared, these x's will cancel out, and you will have negative y over x squared plus y squared. That is a good sign too, because that is exactly what we got by doing the matrix, what do you call it? Inverse of the matrix. Good sign, good sign. So now we have found some independent confirmation that del r del x and del r del y, I should say del, it was theta that I was looking at, that I was concerned about, wasn't it? Del theta del y are indeed these values over here. Through both physical intuition, through inverse matrices, and through the use of derivatives of arctangent, I feel confident of the example, and in saying ta-ta for now.